Thanks for the very kind introduction and for the invitation to be here and to present our research. So my talk is actually going to be a deeper dive into technologies compared to previous talks that you've heard in today's session. And specifically, I'm going to talk about this new era of intelligent neural interfaces for treating chronic neurological and psychiatric disorders. So I'll present some of our lab's work in the past 4 or 5 years in combining AI and integrated circuits toward building more intelligent neural interfaces. So this is the work we have done in my lab at Cornell and more recently at EPFL. So we are all familiar with the neural interface. So these are systems that record brain activity at different spatiotemporal scales. So you can record the spikes, which are high-frequency signals, or, for example, lower frequency ECOG or LFP through these surface or deep brain electrodes. So this is the passive, the electrode part. And then at the core of this system in any interface, there is a neural microchip, a tiny silicon chip, which can record, amplify, and process neural signals, and then deliver targeted electrical stimulation to specific electrodes, as you can see here, in order to modulate the brain, to suppress a symptom, or provide a sensory feedback. So this is what we call a closed loop or a bidirectional interface. So essentially, you can read and write to the brain. So it's a brief intro, and the challenge that we are trying to address in our integrated neurotechnologies lab is how to design more effective and more efficient neural interfaces for a wide range of neurological and psychiatric disorders. And this involves both neuromodulation and brain-machine interface systems. So there are different ways to tackle this problem, but our approach to this is truly interdisciplinary. So we combine integrated circuits with algorithms and AI, and we work in very close collaboration with clinicians. So our goal is to develop a new generation of neural interface ASICs, so these application-specific integrated circuits that are extremely low power and miniaturized, as you can see here, but at the same time, intelligent systems that are safe and effective for chronic use. So in this talk, I will specifically focus on the aspects of designing high-density and intelligent systems, but in our lab, we work also on other aspects like building wireless systems, dealing with artifacts, and so on. So in recent years, both in the academic research, academic institutions, and in neurotech companies and startups, there has been a trend toward building higher channel count systems. So you can see some examples here, like the NeuroPXI probe, the high-density ECOG by Precision Neuroscience, the threads of Neuralink, the polymeric threads, as well as the microwire bundles by Paradromic. So all of these systems promise recording from thousands of channels. And this is, of course, a very exciting time for neurotechnology. So this is promising a lot of new opportunities in this field. But this also emphasizes the need for further miniaturization of the hardware and building lower power systems. In fact, much lower power compared to what we have here in order to develop future human-grade devices. So some of the numbers that you see here are actually not safe for chronic use in humans because we need to minimize the heat dissipation in the brain. And the other important aspect is the integration of AI and on-chip intelligence, which could potentially enhance the capabilities of these devices, but this is still something that we don't see in many of the current systems. And why this is important, so having higher density of electrodes can result in more accurate detection of symptoms in disorders like epilepsy. And if you think about the stimulation, having a higher number of smaller electrodes can reduce the side effects of a stimulation by avoiding the stimulation of irrelevant regions in the brain. And in the context of brain-machine interfaces and motor prosthetics, this can enable more accurate decoding of movement and more natural prosthetic control. So this is kind of the state of technology, but if we look at the devices that are available today, commercially available devices for patients, actually we have very few options, and they are quite simplistic in terms of the technologies that are used in these devices. The deep brain stimulation, or DBS, for Parkinson is a well-known example. And in recent years, we see an interest in building closed-loop systems, like the responsive neurostimulator by NeuroPSI for epilepsy, the VNS device, as well as the Medtronic's Percept, which is an investigational device for movement disorders. And a number of recent also devices which are again focused on movement disorders, like Alpha DBS by Neuronica and Dynamo Systems. And in the field of brain-machine interfaces and BMI, despite a lot of interesting advances, so we heard about it in this morning's talks, we still are lacking clinically viable BMIs as a product that patients could actually use in their daily lives. So if I wanted to actually summarize the limitations of current systems, so these devices currently have very small number of channels, at least the devices that are clinically approved. That means they have a low resolution, and they are also very limited in terms of on-device processing capabilities, which limits their therapeutic potential. Many of these systems are still bulky, wired, and invasive. And the other important point is that we urgently need new devices for many other prevalent conditions like psychiatric disorders, Alzheimer's disease, and so on. So many of these neuromodulation systems are still primarily focused on epilepsy and movement disorders. So with that intro, I'm going to talk about 3 example applications where intelligent neural interfaces can have an impact, starting with an AI-enabled closed-loop stimulation system for real-time symptom control. So this is in the context of epilepsy and Parkinson's disease. And then I'll talk about new paradigms for closing the loop in psychiatric disorders. And finally, I will present some of our latest work on developing intelligent brain-machine interfaces. So we have developed application-specific integrated circuits for these 3 applications that I mentioned, which have been presented in solid-state circuit conferences like ISSCC. So I'll start with the first topic, integration of AI on closed-loop devices. So basically, the idea is that as opposed to conventional approach that the neural signals are amplified, digitized, and transmitted to an external system to do some processing and control the simulator, what we can do is that we can directly integrate the biomarker extraction machine learning algorithm on the implantable system in order to detect these symptoms in real time and activate the stimulator. And this has a number of advantages. So this can result in very effective intervention with low latency. And this is extremely important in these closed loop applications, reducing the latency in closing the loop. This can also reduce the telemetry power because we avoid the transmission of power to an external system during closed loop operation. And finally, this results in better security and privacy, again, because we avoid the transmission of patients' private data. And thanks to the power of AI in decoding and predicting different complex behaviors and brain patterns, this can be used in many different applications. So we can use this for detecting symptoms and stimulation in epilepsy, in movement disorders, even to detect changes in mood in a patient with depression and so on. Or this framework could even be used to decode movement in a brain-machine interface to provide a sensory feedback or enable spinal cord stimulation, as you heard before, and so on. So this is the general framework. And in recent years, we have seen an interest in the IC design, in the integrated circuit design community, in building systems that have integrated AI for closed-loop stimulation, and this has been primarily focused on epilepsy. And the one reason for that is the availability of data from patients with intractable epilepsy. So what I'll do today in this talk is that I'll first talk about our neural tree system, where we wanted to improve the number of channels and the application domain of this closed-loop system. So we wanted to integrate more channels and go beyond epilepsy while maintaining a very low power and area. So you can see that the area per channel for our design is very small. So this is a top-level view of our neural tree system. So this closed-loop device can record neural signals from up to 256 channels. So this is either ECOG or LFP. And depending on the outcome of the on-chip classifier, this can activate up to 16 channel, any of these channels for stimulation for closing the loop. And our system was extremely modular and also versatile, meaning that we can use this in different applications that I'm going to talk about. So this work is funded by my ERC starting grant. So essentially, the problems that we wanted to solve here was the low channel count in existing systems. So for this, we developed a high-density 256 channel analog front end for recording neural signals. So this is an important bottleneck in scaling up the number of channels, as you need to amplify the low amplitude signals with very low noise, and usually this requires significant area. So we had to develop some ideas to shrink the area and be able to do that in a miniaturized way. Second, the limitation is the fact, so we wanted to extend the application of our system, and for that we used a broad set of neural biomarkers and a multi-class on-chip classifier. And finally, to address the hardware complexity, we proposed an energy-efficient classifier, which I'll talk about it, and used extensive circuit algorithm co-design to build our system. So this is the complete block diagram, and there are a lot of circuit details, but I'll try to just comment on some aspects that I think would be interesting for this audience. So one idea that we propose in this design is what we call channel selective inference, meaning that so in the training phase of our system, we want to be able to record high resolution data from up to 256 channels. So this means we activate 4 modules of 64 channel amplifiers during training. But when we want to do the inference, we dynamically select 64 channels out of 256 and activate only 1 module of the front end. And the reason for that is that we usually observe that so in these classification tasks, only a subset of channels contribute to disease relevant activity. So you can see this in this channel importance analysis for seizure detection in a patient with epilepsy. So this means that while we can learn those channels during training, in the inference mode, we can power off some of our amplifiers in order to reduce the energy consumption. So as I mentioned earlier, an important or a challenging aspect of this design was the implementation of amplifiers, because we wanted to have many channels in a very small area. And to do this, we opted to use a time division multiplexing approach rather than the conventional way that you have a single amplifier for each channel. But the challenge that this TDM approach actually brings is that because we are operating at a faster speed, this means that we have a very short time for processing each channel. And the fact that we have in these multiplex systems is that the electrode DC offsets, so the DC signal that we observe at the electrode tissue interface, this can actually fluctuate quite significantly between different electrodes. And here we have a very short time to cancel that DC offset in order to be able to preserve the neural signal. So for this, we developed a new architecture based on a two-step fast settling amplifier, which is able to cancel these DC offsets in 2 steps. So we have a first very rapid cancellation of coarse DC offsets. So we remove the large components of the DC signal, and then we have another fine cancellation loop, which is removing the residual offsets. And this is done in a time division multiplex fashion, meaning that we have only one amplifier that is processing 64 channels. And it's quite different from the conventional approach that we have in almost all medical devices, and is the common practice in the field. So with this idea, we were able to achieve a very low power per channel, as you can see here, 1.51 microwatt per channel, and an extremely small area for each channel, meaning that we can easily scale this up to many, many channels without having significant overhead in terms of size of the system. And this is quite modular, again, because we process every 64 channel with one module. We can easily add or remove some of these amplifiers to change the number of channels that we want to record from. So that was about recording, and the other idea here is the integration of a broad set of neural biomarkers, which are relevant in neural signal classification in common tasks, such as detection of seizures in epilepsy, or detection of tremor in Parkinson's disease, or even for classifying finger movements in a brain-machine interface. So here we have a combination of temporal, spectral, and phase-based features. As we know, spectral energy features are quite common in different applications. In the case of epilepsy, we have time domain features like line length. We have local motor potential for BMIs, and some phase-based biomarkers for epilepsy and Parkinson's disease. And the implementation of hardware, again, so there are many circuit level ideas here in order to reduce the complexity and enable lower power implementation compared to standard designs. So I think we are familiar with the concept of closed-loop stimulation for epilepsy, but I'll just briefly mention why it is also important to do this in the context of Parkinson's disease. So as we know, open-loop DBS is quite effective in Parkinson's disease, but it also has side effects such as gait and speech problem. It can create changes in mood, as well as the high energy consumption and the fact that there may be needs for replacing the battery over time, because this is an open loop system. So the concept of adaptive DBS is trying to overcome those issues by real-time activation of a stimulation based on feedback from patients' biomarkers, from patients' neural activity. So there have been a number of studies pioneered by the group of Peter Brown at Oxford, which actually shows that this adaptive DBS results in motor improvement and actually less speech problems compared to continuous DBS, which is actually suggesting that this is a more effective and also more efficient method of stimulation, because we are delivering less energy to the brain. But the majority of these studies have been based on a very simple idea of thresholding the beta biomarker, so basically filtering in the beta band and thresholding it to activate the DBS. But beta, as we know, this is not a very good biomarker of tremor. So in a work that we published in 2020 in collaboration with Peter Brown's group, so this was led by my postdoc, Lin Yao at Cornell, we actually proposed a machine learning framework for more accurate detection of tremor in Parkinson's disease in order to guide the DBS in an adaptive fashion. So in this work, we used the data from 12 patients with Parkinson's. So these are the LFB recorded through the DBS lead, and we use acceleration signal for labeling. And using a gradient boosting algorithm, we were able to achieve a very good accuracy. And you can also see that as we looked into multiple biomarkers of tremor, we actually observed that many simple and even low complexity statistical biomarkers, like, for example, George parameters, are more correlated compared to beta power, which is actually more commonly used in adaptive DBS studies. So you can see how the output of classifier compared to the ground truth. And this study kind of informed the choice of biomarkers for the hardware or the chip that we later designed. So the design of the machine learning algorithm for our neural tree system, so this also took several iterations. So we started with the work we published in 2018 on gradient boosting trees, as I just mentioned. So this was in collaboration with Azita and Mami at Caltech, where we implemented an ensemble of decision trees for seizure detection. And then later in this work, we proposed a probabilistic oblique tree, or a neural tree model, which is essentially a tree-structured neural network. So we have neural networks within the nodes of the decision tree. And the idea we propose here is what we call energy-aware learning, meaning that we are using the power consumption of features, these biomarkers, in order to regularize our objective function. So what this means is that we are basically penalizing those features, for example, phase-based or spectral features, which consume more power compared to simple features like line length, in order to encourage our model to use a higher number of those low-power features. And this results in a significant reduction of power with a marginal effect on accuracy. And our probabilistic model is also compatible with gradient-based optimizations, meaning that we can aggressively prune our model to reduce the size of the on-chip memory. So the algorithm design was done by my PhD student Bin Zhou. This was also supported by a Google AI faculty award. So you can here see this dynamic channel activation that I mentioned along the decision path of the tree as we reach the dominant class. So here we can support up to six class tasks with this single neural tree model. And the hardware is also quite simple. We are using a single multiply and accumulate unit for all the feature weight multiplications in our system. And finally, we also integrate a 16-channel neurostimulator on the same chip. And the reason we have lower channel count for stimulation is that integrating high voltage stimulation in standard CMOS process is quite challenging. So we had to deal with the large area of design and propose some techniques to be able to shrink the area. But it's still, the number of stimulation channels, as you can see, is much lower than the recording channels. So here you can see examples of the output of the classifier that is integrated on the chip. So for this, we used several publicly available data sets, such as the CHB-MIT EEG data and intracranial EEG data set for epilepsy, as well as the LFB data from DBS leads from Oxford, which was used for detecting the tremor. So you can see examples of the output of classifier and the overall performance. We also validated our system in vivo in collaboration with the group of Stephanie Lacour at EPFL, who built this soft micro-ECOG array. So we implanted these electrodes in rat models of epilepsy and verified different functionalities of the system. So you can see, for example, this increase in temporal and spectral features at the onset of seizure. So if I compare this with previous systems that integrated machine learning for neural interfaces, so our design was the first that was able to integrate a very large number of channels, and we did this while significantly reducing the area per channel and also improving the energy efficiency of the system. So our system was also extremely low power, consuming 453 microwatt, the whole system. And this is despite the fact that we have a broader set of biomarkers that can support many different applications. So the IC design work for this was done by my PhD student Yusuf and Chong. And just one last comment about this part is that we also explore other more recent machine learning algorithms and latest models in order to further improve the accuracy of our classifiers. So in a recent work, we have been looking into dynamic graph-based models that can actually capture the spatial and temporal characteristics of EEG in order to detect the onset of seizure. And this is the work that gave very good results, and we are going to present this in the ICML later this year. So that was the first part. And so in the second part of my talk, I'm going to discuss about neuromodulation devices for psychiatric disorders, which, as we all know, are affecting millions of patients around the world. So this is really a major problem. So you can see some numbers here. So depression is one of the leading causes of disability, and these numbers, or the prevalence of these disorders, continues to increase. And really, the challenge is that many patients are out of options. And while we need many, new innovations in this field, surprisingly, in the device development, I think there are very few efforts that have been done, maybe because this is a very complex problem. So the conventional open loop DBS has shown some promising results in patients with treatment-resistant depression. So different brain regions have been studied, but there has been also some mixed results and some variability in terms of efficacy in these trials. And the reason that this open loop DBS actually may not be very effective in psychiatric disorders could be that these psychiatric conditions actually involve multiple distributed networks in the brain. So they are more complex to tackle. So the basic problem is that if you look at current treatments, they are not actually targeting the mechanism of disease, and they are not showing any proof of target engagement. And this could be also because these psychiatric conditions actually arise from communication failure between multiple distributed regions in the brain. So an approach that is based on open loop focal DBS may not be very effective. So we have been working on a project that is funded by the National Institute of Mental Health in collaboration with Dr. Alec Quirich, who's a psychiatrist at University of Minnesota. And our goal here is to develop a new implantable neurostimulator which can control and potentially even correct the disrupted communication in disorders like mood and anxiety. So one of the ideas that we propose in this system is the concept of phase-locked stimulation. So implementing this on the device is something we propose here. And what this means is that we can actually stimulate one region in the brain at particular phases of neuronal oscillation in another region. And there's increasing evidence showing that this method of stimulation results in more physiologically meaningful effects in a way that is more long-lasting because of improving the plasticity. And there are a number of groups that are trying this with non-invasive methods and also in coupling with TMS and so on. So this is one idea in our system. And the second one is measuring the neuronal synchrony. So as we know, and you heard also in the previous talk, different brain regions actually communicate through these neuronal oscillations. And in disorders like depression and even Parkinson's disease, the degree of cross-regional synchrony, this can actually be a key indicator of the pathological brain state. So this implies that if we could measure biomarkers or metrics that can quantify the level of synchrony or coupling between different brain regions, such as phase locking value and phase amplitude coupling, so then we can use this in order to improve or suppress symptoms by regulating the level of synchrony through stimulation. So this is the second idea in our system, that we integrate these, I call them network-based biomarkers in our implantable system. So based on these ideas, this is the first prototype of the system that we developed. So here we can record neural signals from two regions in the brain. So this could be DBS leads or other types of electrodes. And we have a 16-channel neural recording circuitry and analog to digital conversion. And then the output is sent to an FIR filter for bandpass filtering and Hilbert transform to extract the real and imaginary parts, which are then used in phase and amplitude envelope extraction, and they are passed to the synchrony processor in order to extract those biomarkers that depend on the value of phase. And based on the symptom, based on the stimulation strategy, we can use one or a combination of these biomarkers to threshold and activate the on-chip neurostimulator. So I skipped the details of hardware, but just comment on one key idea here, that was the reducing the complexity of phase extraction, which is because this is the core function that we have in our system in order to deliver phase-locked stimulation or to extract these phase-based biomarkers. And for this, we used a first-order arctangent approximation algorithm and a very simple lookup table in order to compensate for these periodic errors, and implemented this with very efficient hardware. And this resulted in very low errors. This is sub-LSB error for different combinations of real and imaginary part. And this is verified in vivo. You can see the phase extracted by our lightweight LPE hardware compared to the ideal phase extracted in MATLAB. And once we extract the phase, we can use that to implement these biomarkers like PLV and PAC. And again, we use a number of techniques here to reduce the complexity in terms of power consumption and area. So I'll explain in the next slide how we did the in vivo testing. But here you can see that we have a very good matching of the these PLV and PAC that are extracted by our system on chip compared to the ideal biomarkers that are extracted in MATLAB. And this is the output of chip, including the amplifiers in the system. So to test this in vivo, we did extensive testing. So we implanted two microwire arrays in the infralimbic cortex and basolateral amygdala in the IL and BLA regions, which are involved in fear expression. So they could be important in disorders like anxiety. So here you can see the experimental results. So for example, here you can see the output of our amplifiers on the chip compared to the commercial intent system. So we achieve sub-microvolt RMS noise performance with a very low power. And we were able to verify the closed loop functionality with two different scenarios. So in the first setup, we are recording the phase of LFP in the IL region, and the simulation is actually locked to 180-degree phases of this IL theta. So you can see these biphasic pulses that are generated at the output of the stimulator. And in the second experiment, we are locking these pulses to both phase and PLV. So this means that we are stimulating again when this phase is crossing a target value, but also when our PLV, this cross-regional PLV, is within a certain threshold range, which is a therapeutic window that could be programmed by a physician. So we have these pulses of stimulation generated at the output. And we have also an option to create the pseudo-random phase thresholds for intentional disruption of synchrony, which could be useful in treating certain psychiatric conditions. So this entire system was implemented in a chip with 2.24 square millimeter area, consuming 60 microwatt of power. And this is the first chip that enables phase-lock DBS with a combination of different biomarkers of synchrony with extremely low power. And this is important because this could be potentially used in treating network-based disorders which disrupt communication between different brain regions. So we've been doing extensive validation of this our algorithm and hardware, and now we are integrating our ASIC into an implantable stimulator and hoping to plan for in-human testing in patients with treatment-resistant depression within a few years. And just one last comment about this part. So it's also possible that to further improve the efficacy of closing the loop in psychiatric disorders, we could also combine this with an on-chip decoder of, for example, mood state, which could guide the output of guide the activation of phase-locked DBS to further improve the efficacy in these systems. So this wraps up the second part, and the last topic is about some of our recent work on developing intelligent brain-machine interfaces. So I will also skip the introduction given the great talk we heard from Richard. I'm just going to talk about one aspect about using AI, and so I think in recent years, similar to many other domains, AI and machine learning has made a significant impact in the field of brain-machine interfaces. So you can see some of the breakthrough studies that are partially enabled by the power of AI. So the first example is from Richard's group. So we have systems for enabling control of robotic arms, restoring walking in patients with a spinal cord injury, and even attempts to decode the lost speech or handwriting. So these are really breakthrough studies that show the potential, the great potential of these technologies. But eventually what we really hope is that, so most of these systems are still kind of tethered, systems that rely on external computers for processing, that are power demanding, they limit the mobility of the patients, and these are not solutions for everyday lives of patients. So the hope is that in the future, these brain-machine interfaces would be fully implantable and miniaturized systems that would be more convenient and efficient for the patients, and also intelligent, so that they could maintain a good performance over long periods of time. So if you look at the developments in the IC design domain, there have been some efforts to integrate algorithms specifically for spike sorting in integrated circuits, as you can see here. But as we know, spike sorting alone is not sufficient to decode movement intentions. There have been also a handful of SOCs that integrated algorithms for decoding movement intention. So you can see there's some examples. Our neural tree chip is one of them, which are primarily focused on simple BMI tasks like classifying finger movements. But similar to spike sorting, this is a relatively simple task. But if we think about BMI and so the more complex BMI applications, they would actually require much higher number of classes and more advanced algorithms compared to, for example, the clustering techniques that you can use in spike sorting. So current systems focus on simple BMIs. The complexity of hardware is also an issue, especially when we want to scale up the number of channels. So we need to be able to develop hardware and algorithms that would be scalable to support higher density of electrodes. So in an effort to build an implantable BMI chip, we were interested in this recent BMI system that enabled rapid communication recovery through decoding the handwriting and the speech. And specifically, we focused on the first system thanks to the availability of data from Chen lab, which allowed us to actually explore some algorithm and hardware design for this application. So we wanted to see if we can actually design a chip that could translate the brain activity associated with handwriting into text, and we wanted to do this with a simple and low power hardware. So as you know, in the original system from Chen lab, so they used a recurrent neural network to classify 31 characters from intracortical signals with 2 Utah array, and achieved a good accuracy of 94% and higher speed compared to previous BMIs, which decoded point-by-point movements. But the model that they used here was a complex RNN with a very large number of parameters, which is not suitable for hardware implementation. So we wanted to develop an alternative model that would be actually feasible for implementation in low-power platforms. And for this, we developed a brain-inspired algorithm. So this is basically inspired by the way that our brain selects visually salient objects. So when we look at an object, our brain actually creates a class saliency map, which highlights the most visually distinctive objects and kind of draws our attention toward that. So in a similar way, here we extract neural codes. So we call them distinctive neural code, or DNC. So these are signatures of brain activity that best actually represent or distinguish the brain activity for each class, and we can use them for decoding the neural signals. And using this approach, this allows us to achieve very effective extraction of information in a very interpretable way. This results in significant reduction of dimensionality. And thanks to extraction of information with this approach, we can use a very low complexity decoder with significantly lower number of parameters. So I briefly explained the details of this system. So this is the idea of this brain-to-text, DNC-based brain-to-text BMI system. So the neural signals, so we use the same data recorded from, again, the original study. So the neural signals are processed, so there's some spike detection and thresholding. And once we smooth these spike rates, this is passed to a DNC-based decoder, which is compressing the high-dimensional data into a low-dimensional DNC space, which is then decodable with a low-complexity classifier, such as LDA. So in this case, we use a simple LDA to classify the 31 characters. And this results in significant reduction of dimensionality in different steps of process. So I'll talk about this in the next slide. And much higher compression, over 150 times more compression compared to previous BMIs that use the spiking band powers. And despite this significant dimensionality reduction, we achieve a very good performance of 91.3%, which is comparable to the 94% of the original design with significantly lower complexity. So here you can see a little bit more details. So our system has a neural recording chip, which can capture 192 channel neural signals. So these are broadband neural signals. And then we also have a neural decoding chip. So this system is a chipset. So we have two separate chips that are responsible for recording and decoding neural signals. And in the decoder, we have, so essentially, so this can receive 512 channel spike rates as input, which are then smoothed, so they're convolved by a Gaussian kernel to reduce the sensitivity to temporal misalignments. And this is passed to onset aligner. So our decoder essentially detects the onset of task-relevant activities and aligns the input spike rate with that onset, and generates timing signals for the DNC unit, which is actually trained offline. So the way that we train our system is that the DNC and LDA are actually trained offline, and we store parameters to the chip, which are then retrieved during the online operation. And then this DNC unit extracts these salient features and passes them to an LDA classifier, which eventually predicts the output class. So this process repeats every 1 second, so we can decode 60 characters per minute with this particular design. So unfortunately, I can't explain all the details, but the key idea here is this the concept of DNC, where we propose this new class saliency model, which measures both the magnitude and also the uniformity of between class distances in order to find the most informative or most important features for decoding, which are then used by the simple LDA to find the output class. And this is every 1 second after the onset, the detection of onset, we have one output class predicted by the chip. So here you can see the visualization of neural activity in a 3-dimensional DNC space, where we have this nice separation of activity for most characters that are shown here with only 3 DNC dimensions. And in the case of some characters, we may need a higher number of DNCs to separate these activities. So our DNC-based decoder systems, as you can see, we have the recording and decoding chips. So this is fabricated in a 65 nanometer process. The entire system consumes 883 microwatt, where the decoder consumes around 220 microwatt. And we verified this with the pre-recorded human data from the study that I mentioned. So you can see the ground truth and the output of the chip, and also verified this across 10 recording sessions, where we were able to achieve an accuracy of 91% for the decoder and 93% for the software model of our system. And this is using only 100 dimensions of DNCs, which is much better than using, for example, a correlation-based approach for selecting these features. We also verified this in vivo in an auditory stimulation experiment, where we used a 384-channel NeuroPixels probe, and the goal was to classify 6 different frequencies of stimulation using the decoder chip, where we achieved an 87% accuracy. And we separately verified our neural recording chip, and we were able to record actual intercortical signals. So we didn't have access to the raw data, so the validation of the system in both cases was the decoder chip was separately validated with the digital input data. So the contribution of this design was, I think, that the fact that we were able to significantly increase the complexity of BMI task that we implemented on the chip, and this was achieved with significantly higher number of channels and more efficient area and power compared to previous designs. So with that, I would like to acknowledge my team of students, our funding sources and collaborators, and thank you very much for listening.